Okay, hello everybody. So, first question. Physically, what is a curve? What is velocity? What is acceleration? Okay, so what is a curve? So a curve is like that. This is a curve. And in particular, what I'm thinking is like, this is a bird flying through space. So moving in time is often the case, but it doesn't need to be. And so this is a curve. You could just think of the actual curve here, or you could think of something moving along it with different speeds. Then you could imagine something going very slow and then speeding up, or you can imagine something going fast and then slowing down. And then you get sort of different things. So yeah, this is a curve. Velocity is like, even though your curve is curvy, at a given moment, we imagine that there's an instantaneous velocity. It's your instantaneous rate of change. And it has a direction and a length. So here I drew the velocity at this point. But if I was going faster, maybe the velocity would be like that. If I was going slower, maybe it would be like that. Over here, the velocity is pointing in a different direction. And down here, it's pointing in a different direction. Over here, it's pointing right along the x-axis, or the first axis. Acceleration, then, is what's acceleration? So acceleration, so here's the velocity at that point. But the acceleration would be the change of the velocity. So here we can see that the velocity is going to start turning and turning up. And so the acceleration at this point would be pointing that way. Maybe it's even pointing that way. Maybe this velocity vector is going to change very quickly. Like, whoop, it changed over there. Okay, so that's physically what it is. Mathematically, what is a curve? What is velocity? What is acceleration? Mathematically, how do we encode these information? So, a curve is a map. It's a function. Remember, map and function are the same word. Often it's called gamma. And if it's a space curve, then it goes to R3. If it's a plane curve, it goes to R2. It can go to Rn. In fact, we'll see curves in R6 to describe planetary motion. But this one right here maps from R to R3 in our first example. And so that's the curve. Here's a curve. Here is a curve mapping from R to R2. So this is a plane curve. In fact, this will give an ellipse. And by the way, like I haven't told you this, but you were supposed to assume that A and B are fixed real numbers. For example, if A is like 4, then this would be a length 4. And if B is 2, then this would be a height 2. So that would be this is an ellipse, and this curve is our familiar twisted cubic, which I drew up here. What is velocity? Velocity is another map. We usually call it gamma dot. This is usually in physics they say that, or gamma prime is often used elsewhere in math. But I like the gamma dot. And it's again just another map. Because what we do is we produce another map setting t to the derivative in each component. So all I did was just treat each component separately, each dimension separately, and take the derivative of each. And this gives a new map. So we could literally think of this as like a new curve. But it turns out that a better way to think about it, velocity is another map with gamma prime at a moment, like gamma prime at t, the velocity vector attached to the original curve, at gamma of t. Okay? So that's we evaluate this like gamma prime of 1, we plug in t equals 1 and get 1, 2, 3. And that means that over here at gamma of 1, is this point here, we could think of it as this vector, we'd have a velocity vector, and that is gamma prime of 1. In this case, it happened to be 1, 2, 3, whereas gamma of 1 was 1, 1, 1. Right, 1, 1, 1, plugging in at t equals 1, 1, 2, 3, plugging in at t equals 1. Acceleration, then, is the same thing as velocity, but 2 derivatives. So, we can see it as another map where, again, we're mapping t goes to, now this time 0 to 6t. And this we'd say is gamma double dot, or gamma prime prime. Doesn't matter what you name it. Remember, naming is up to you. There's some conventional names that you should know. But yeah, it's sort of up to you what you actually name it. And then the acceleration at a point would be like, gamma double prime at the time t equals 5 is a specific vector, in this case 0, 2, 30. So like a lot of acceleration in the upward direction, which makes sense because this curve is very quickly twisting upwards. So let's just see, what's gamma prime. In this case, it'd be minus a sine t, b cos t. Gamma double prime, so I like to, sometimes I put the name of the map above it. Gamma, oh wait, this is only gamma prime. This is gamma, gamma prime, gamma double prime. And so now I take another derivative. Derivative of sine is cos. Derivative of cos is minus sine. And that's the acceleration. Okay. What does the cross product do? What does the cross product do? How to compute the cross product? Sort of 2 questions about something called cross product. So the cross product is of 2 vectors. Cross product of 2 vectors. So it eats 2 vectors and it'll spit out another vector. So it's now again in R3. And cross product only works for R3. And okay, so what does it do? The cross product of 2 vectors gives another vector. Compare that to the dot product. The dot product of V and W gives a number, even if V and W are in Rn. And the dot product can take any vectors in any size space. The cross product only takes vectors in R3 and gives another vector perpendicular to them. Perpendicular to both previous vectors. Okay, vectors. Okay, so if V and W are 2 vectors, maybe they're here and here. Maybe this is V, maybe this is W. Then you can imagine that they span a plane together, and V cross W will be orthogonal to that plane. So this is hard to draw, but these are supposed to be orthogonal vectors. So like if V was there, W is there, then V cross W might be there. And it might have a different length. It might be short, it might be long. And we're going to see how that works in a moment. So how do we compute it? So the way we compute it is we take I hat, j hat, k hat, then the components of V, and then the components of W, and we compute the determinant of this matrix. I like to write det of the matrix. but some people just do straight lines, like absolute value almost around it, and that to them means take the determinant. So we know how to do that. There's these patterns, like here, 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 here. This gets a plus, plus, plus. Oh no, that's a minus, so I did this wrong. There's the previous video on determinants, but basically, actually, let's learn a different way to do determinants. So a determinant has 6 terms, but one way to organize them is look at the I hat term and see that it'll come here with a plus and here with a minus. So what we'll have is I hat times 1 times minus 3 minus 0 times 2. Then we'll have j hat times, and j hat will get these 2 with a plus and these 2 with a minus. So it'll be 2 times 5 minus 1 times negative 3. And then k hat will get these 2 with a plus and these 2 with a minus. So it'll get 1 times 0 minus 1 times 5. And so the end result here is I hat times minus 3 plus j hat times 10 plus 3 plus k hat times 0 minus 5. And remember, I hat, j hat, k hat are just the vectors in the first, second, and third components, which we also call E1, E2, E3. And so, at the end of the day, this is going to be the vector minus 3, comma, 13, comma, minus 5. And this is V cross W. Okay. Now, that's all I want to say for cross product right now. Maybe I'll say a couple other things briefly. V cross W and W cross V. They're not the same. It turns out they are negatives of each other. So V cross W is the same as minus the vector that you get from W cross V. And then they do have like linearity in the sense that if we take 3 times V and then cross it with W, what we get is the same as if we did V cross W and then multiplied that vector by 3. And I don't want to dwell on the cross product too much because it only works for R3. It's going to come up in your physics classes, but mathematically it's sort of like a coincidence, an anomaly. It doesn't generalize to higher dimensions, and so it's not as fundamental. If you want to see how it really comes up, I would look up something called geometric algebra. I would look up something called de Rham cohomology. I mean, there's really a lot of math here. I would look up something called Lie algebra of the rotation group. And all of these things are sort of ways you could generalize the cross product or understand the cross product. And none of them should we cover in this class. And so I'm not even going to attempt to give you an understanding of the cross product. I'm just going to say it's a convenient way to get another vector that is perpendicular to 2 previous vectors. And that's sort of it. That's all I think you should know. I don't think you should worry about anything else until a different time in your life. Okay, great. What is the TNB frame of a curve? This is also called the Frenet-Serre frame of a curve. So we have some curve, let's say in space. What's its TNB frame? Turns out it'll be like a little vector there, a little vector there, and a little vector there that's orthogonal. They're all mutually orthogonal. It's a little coordinate system that moves around with you as you're on this curve. And so the best way to see this is in an animation. So I recommend looking at the Wikipedia page, not reading it intensively because there's a lot of extra things that we won't need, but here's the TNB frame of this curve. And you can see how it sort of moves around with the curve. And oh, here's a nice animation of the TNB frame. So it's like if you were actually in a spaceship traveling on this curve, then you, this would be like your coordinate or reference frame. Like to you, straight ahead is always the t vector. To you, straight ahead is t. To you, to the left is n. Actually, that's your acceleration as well, sort of. And then b is always, I guess, up. And so let's actually do this together. So GeoGebra.org, I'm going to go to the classic GeoGebra. And let's do this for a, let's make a curve, and let's have it be an ellipse. So we're going to take about 4 cos of t times 2 sine of t. And we're going to say the variable t goes from 0 to 2 pi. This is just the syntax in GeoGebra. Okay, how do I get rid of this? Okay, good. So there's my ellipse. And then what I'm going to do is I'm going to look at a point. So this has created a curve called A. So I'm going to put, first let's calculate the velocity vector. Now, to create a vector, we could just give a point, and then it'll create the vector that goes from 0, 0 to that point. So if I gave it like 2, 5, it would go from 0, 0 to 2, 5. I mean, I'll even just show you that, 2, 5. But I actually don't want that. What I want is a vector that starts at a certain point and ends at another. I want it to start at a of s. And now, because I haven't defined s, GeoGebra will create a variable s as a slider later, and it'll move me along the curve. S is like t, it's just another variable. I already used t up here, so a of s, and then I want the end point to be the start point plus the velocity. Will this work? There we go. So now you can see the velocity vector. As I'm moving around the ellipse, it gets faster near here, slower near this left side. And that's the velocity. Of course, this is going, okay, let's figure out how to make that go only forwards. Slider, increasing. Okay, and now we can, now it'll move forwards. And you can sort of see the velocity gets longer when we're at the top and bottom. We're going faster there, and shorter it goes when we're at the sides. We're going slower there. And you can imagine that this is something orbiting around, let's say the sun is at the origin. Okay? And now let's create another vector. Let's take the acceleration vector. And I want the start and end. So I want to start at my point on the curve, and I want it to end at my point on the curve plus the acceleration. And so now we can watch. And you see that elliptical orbits do happen in if we're on a planet. We're always being attracted to the sun. So our acceleration is always pointing directly at the sun. And so this sort of makes sense. Now notice, the acceleration and tangent, they are not at 90 degrees. Usually they're not at 90 degrees. Sometimes they might be. But like right there, I think you can see it's a little smaller than a 90-degree angle. So I want the TNB frame to be orthogonal, so I'm going to have to do something to this velocity vector, to this acceleration vector, a double prime of s. What am I going to do? Well, I'm just going to remove the component along u. But also, okay, well first let's create this vector. Let's create the unit tangent vector. So I'm going to start at a of s, and I'm going to end at a of s plus a unit vector in the direction of velocity. So a of s, and then my final point will be a of s plus a unit vector. I'm just going to, it's sort of like normalizing the velocity a prime of s. And so you can see what I've made is this new vector w. It's just the same vector u, but normalized so that w has length 1. So I can even turn off u. Now you can only see the unit tangent vector. Okay, so there's the unit tangent vector. And now I want to do the same thing to, well first, okay, now you can see this angle is not 90 degrees. I'm going to remove the component of v in the direction of velocity. And so we learned how to do that. So I'm going to create a vector that starts at a of s, and ends at a of s plus, and now I'm going to take the acceleration and remove a piece of the velocity, namely the piece that is in, well, here's the formula. We've learned this formula. A prime of s. So this formula is incredibly useful. I'm taking the acceleration and I'm removing its component in the velocity. A double dot, removing, subtracting off a certain amount of the velocity vector, so that what I'm left with right here is a normal vector, and you can see it right there. Okay, so there's that vector. And oh, it even serendipitously, well no, it should be n. This is the vector n in TNB. And now I need to normalize it, so actually what I can do is, instead I'll take a of s plus, and now I want the unit vector in a double prime of s minus a prime of, s. Some amount of a, I'm removing this component, so I do the dot of a double prime of s with a prime of s divided by the dot of a prime of s with itself. And now I have this unit vector over here, so I'll turn off my other ones, turn off v, and here I have, let's go up here and click play. Here's my TN frame. TN frame. Now, this is a plane curve. So in 3 dimensions, we need a third dimension for, we're moving along in our spaceship and we want to know what is the orientation of the world for us. So I need a third dimension when I'm a space curve, when I'm in, when I'm in 3 dimensions. I need a b vector, and that b vector should point orthogonal to my unit tangent and orthogonal to my unit normal vector, which really are called t and n, but here they're called w and c. And so we can do that in 3 dimensions. And the way we will do it is we're going to take t cross c, and that'll just produce a new vector, and that will be our third vector in our little TNB frame, which looks like that in 3 dimensions. T for unit tangent, n for unit normal, and remember we produced n from the acceleration gamma double dot, and we removed the tangential component so that it was normal to the tangential component, to the velocity. And then to get b, we're just going to take t cross n, and that'll produce b. Okay, so that's the TNB frame. Yeah, here's t and b. So t is the unit vector tangent to the curve, pointing in the direction of motion. N is the unit normal vector, blah, 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 blah. Just, it has to be normal. B is I guess they call it binormal. I don't know, it's just the third vector because you need three vectors for 3 dimensions. And they take it to be the cross product of t and n. But you don't need it, like the cross product has nothing to do with this. What has something to do with it is you need this third vector to be orthogonal to the other 2 so that you have an orthogonal reference frame. You have a framework for, where are you and what is everything else around you as I'm traveling around through space. And so the cross product is just a way to achieve a third vector b that's orthogonal to n and t.